we go. Force. Force is the agent of change. However, the measurement of change is work. Consider for a moment, when you say you put in work, work isn't just doing something. Work is a measurement of what you did. Work is going to be the product of the horizontal component of force and the amount of displacement experienced by an object. Now, by the way, this displacement will be parallel. So we're talking about an object that's experiencing a force, and that force is parallel to the movement in which it's going. Okay, so if it's displacing, the force is parallel to that displacement, not perpendicular, parallel. By definition, then, we have work is force times displacement. If I were to go ahead and draw an example of this. So here we have an object that has been displaced, and what displaced it was a force. So there was work done on the object by the force. We have this new formula, of course, and the unit for force is a Newton. The unit for displacement is a meter. So I propose to you that a joule, the unit for work, is equal to a Newton meter. In other words, anytime you see a Newton meter, it's the same as a joule. Here's a graph. A spring exerts a force as shown on a graph. How much work is done as the spring stretches from 20 to 30 centimeters? First, we must recognize this in centimeters, and if we're going to actually use this, we're going to have to convert it into meters. Now, in this case, the area of a force versus displacement graph is going to be work. Think about it. If we multiply a Newton by a meter, we get a joule, and a joule is a unit for work. Split this up into two shapes. This rectangle right here, it's going to be, the rectangle will be 40 newtons times 40 to 20 is 20 centimeters, but I need to convert this 20 centimeters into meters. It's going to be 0.20 meters. And then I have this triangle up here. The height of this is another 40 newtons. And it happens to also be 0.20 meters. If we put those together, we get the total area, we get the work. So 40 times 0.2, that's going to give me 8 joules. And then the triangle is going to give me 4 joules. So the total work done is going to be 12 joules.
Perfect.
If we give you a graph, make sure you do the area. If we give you a graph of a force versus displacement, then you will do the area. Okay, which is what we just did here. We did a rectangle and a triangle. A box is pushed by a 2 Newton force. How much work is done on the object? Well, we have a 2 Newton force. We have a 10 meter displacement, and that's 20 joules.
Most impressive.
Be aware that this force that was pushing it displaced it, right? And this force was parallel to the direction of the displacement. A box at rest is pushed by a 2 Newton force. Here we go again. It begins to move. So it starts from rest. It sounds like a kinematic. It accelerates at a rate
again, please?
of 0.8 meters per second squared to the point where the velocity becomes 4 meters per second. Now, you know, the only thing we've looked at today so far is work, is force times displacement. There's no room for A's or V's or anything like that. So we're going to have to go ahead and find displacement. You will, based on what they gave us, right, we do the 3, 2, 1, starting from rest.
Here we go.
It accelerates at this rate. And the final velocity is this. we do want the displacement. So we need in order to calculate the work done. This is the third kinematic.
Could you say that again, please?
Perfect.
Could you say that again, please?
And we've spent countless hours on discussing kinematics. But long story short, if you were to go ahead and solve this for delta x, you're going to get this.
Perfect.
And if we were to substitute these values in and work with the units, you're going to end up getting a displacement of 10 meters. So I'm going to have this force of 2 newtons times the displacement, which I found is 10 meters. And ironically, we get the same thing as the previous problem. Again, notice that this force, that this box was being pushed with a force that moved it in the parallel direction, the same parallel direction as the displacement, that occurred. Okay. Part C. A 20 Newton box is moving along a frictionless surface at a constant rate. While displacing, a 2 Newton force is applied perpendicular to the box. So in the previous problems, parallel was the big issue. Parallel allows us to do work is force times displacement. If it's perpendicular, no work is being done on this object. Okay, because if you think about it, if an object is moving in this direction, okay, and all of a sudden I push down on it, this force, this pink one that I drew, is not displacing it in the y-axis, and is not doing anything to help it along the x-axis either. Okay, so if I apply a perpendicular force, the displacement is not going to, in this case, the displacement is not going in this direction. It's going in this direction. And so this displacement would be due to this force. This force does not work on the object. So how much work is done on this object? 0 joules by this perpendicular force. Take a second to summarize. As long as an object displaces while it experiences a force, is work being done? It is a trick question, so think about it.